Welcome back to Differential Calculus. I'm your tutor Ryan, and today's lesson is going to be on the actual usage of the limit laws in real-life questions. Let's get started. Here are the 11 limit laws from the previous video, and here are the examples for this video. There is an example 7 later in the video, and don't worry, we will get to that. Alright, so example number 1. We have the limit as x approaches 2 of x squared minus 4x plus 3. So by rules 1 and 2, we can split that up into the limit as x approaches 2 of x squared minus the limit as x approaches 2 of 4x plus the limit as x approaches 2 of 3. From there, by rule 3, we can split that up into the limit as x approaches 2 of x squared minus 4 times the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. From here, using rules 7, 8, and 9, we get 2 squared minus 4 times 2 plus 3. And the answer for the limit as x approaches 2 of x squared minus 4x plus 3 is equal to -1. Alright, example number 2. Determine the limit as x approaches -2 of x squared minus 4x plus 3, all divided by 1 minus 4x. Via rule number 5, we can split the limits of the quotient and denominator to the top and the bottom, as seen, and then by rules 1, 2, and 3, we can split it into the limit as x approaches -2 of x squared minus 4 times the limit as x approaches -2 of x plus the limit as x approaches -2 of 3, all divided by -4 times the limit as x approaches -2 of x plus the limit as x approaches -2 of 1. And via rules 7, 8, and 9 together, in the third line, we have -2 squared minus 4 times -2 plus 3, all divided by -4 times -2 plus 1. This equals 4 plus 8 plus 3 divided by 8 plus 1. So therefore, the answer to the limit as x approaches -2 of x squared minus 4x plus 3, all divided by 1 minus 4x is equal to 15/9, or rather 5/3. Alright, we're going to move on to example 3. Alright, example number 3 is a little bit more tricky, so we need to pay attention. It's asking us to find the limit as x approaches 2, and as you can see on the bottom, the denominator is x squared minus 4, but if we plug in an x there, we're going to get 4 minus 4, and we're going to be dividing by 0. So by direct substitution, we're getting a non-favorable outcome. So we may need to factor the cubic in order to solve this problem. So if you don't already know how to, I'll teach you a cool little trick in order to factor cubics, or factor anything really, as long as it's a polynomial. This works. So in order to factor the cubic, we set it up as such, with the denominator to the left side, the dividing bar, and then the quotient underneath the dividing bar. And the process goes like this. The first part of the quotient and denominator are compared. In order to obtain the x cubed we have in the quotient, we're going to need to multiply the denominator by x. When we do that, we get an x on top. Now we multiply x squared minus 4 by the x and subtract it underneath as seen. We get x cubed plus 0x squared minus 4x. What we're left with is 5x squared minus 20 after subtracting. And now we have to compare the x squared and 5x squared term, because we want to eliminate the 5x squared term. And in order to make an x squared into a 5x squared, we multiply by 5. So we put a 5 up top, and we start subtracting. We multiply the x squared minus 4 by the 5 up top, and we're going to get 5x squared minus 20. And when we subtract the 5x squared minus 20 from the 5x squared minus 20, the remainder is 0. Due to the remainder of 0, we can determine that factor of x cubed plus 5x squared minus 4x minus 20 is perfectly x squared minus 4 and x plus 5. You can check it on paper. The remainder of 0 reveals this. Alright, now we're ready to tackle this problem. We have the limit as x approaches 2 of x cubed plus 5x squared minus 4x minus 20, all divided by x squared minus 4. We can split the quotient up into its factors, which is x squared minus 4 and x plus 5, And the x squared minus 4 on top cancels with the x squared minus 4 on the bottom, leaving you with the limit as x approaches 2 of x plus 5. And subbing in a 2 for the x leaves you with 2 plus 5. So therefore the limit, for example number 3, is equal to 7 at x equals 2. Below I've done a quick little drawing illustrating the equation f of x equals x plus 5. And you can see at the point 2, 7, there is a little hole there. That means that at that very location, at x equals 2, there is no direct point. The point doesn't exist, and that's due to the original equation at the beginning of example number 3. Keep that in mind when plotting things like this. Alright, example number 4. The limit as v approaches 0 of 1 plus v, all of that squared, minus 1, all divided by v. Now we can see a problem. V goes to 0, and on the bottom we have a v, so we're going to be dividing by 0 again. So in order to fix this problem, we're going to have to FOIL out the top and see what happens. Let's do this. FOILing out 1 plus v squared gives us 1 plus 2v plus v squared. So that gives us the limit as v approaches 0 of 2v plus v squared divided by v, because the 1's go away. After this, we obtain the limit as v approaches 0 of 2 plus v, because the v on the bottom will cancel out with one of them on the top. And the result of this, after plugging in v equals 0, is 2. Alright, that was pretty simple. Nothing hard about that. Let's move on to example number 5. Example number 5. The limit as v approaches 0 of the square root of v squared plus 4 minus 2, all divided by v squared. So again, here we can see that v goes to 0, so we'll be dividing by 0 again. And in order to avoid doing this, in equations like this that are set up like this, we can multiply by the quotient's conjugate in this case. It could be the denominator's conjugate, you just have to look for it. And the process is like this. In order to find the conjugate, you're going to have to do a lot of work, flipping the sign from a negative to a positive or a positive to a negative. Therefore, the conjugate is the square root of v squared plus 4 plus 2. So, we'll go ahead and we'll multiply through the original equation, top and bottom, by the conjugate, which means all we're really doing is multiplying through by 1. So we're not actually doing anything that changes the equation drastically. It'll look different, but it's the same. And it looks like this. Alright, so after performing this, we're left with the limit as v approaches 0 of v squared plus 4 minus 4, the 4's go away, divided by v squared all times the square root of v squared plus 4 plus 2. The v's on top and bottom go away, leaving you with the limit as v approaches 0 of 1 over the square root of v squared plus 4 plus 2. And plugging in the limit of v becoming 0, we get 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, which is simply equal to a quarter. Alrighty, unfortunately the remaining slides take this video well over 10 minutes, so therefore we're going to save the rest of them for a part 3, in which we're going to tackle a few more things, some which are complicated and some which are not exactly. So stay tuned for part 3. Don't forget to like, save to your favorites, comment, anything like that. It always helps me out. If you're still confused about the limits after this is all done and said for, let me know. Maybe I'll do another video clarifying some things, but you guys are going to have to be specific. Alright, stay tuned for part 3.